All right. So here's number 4. So the first thing I want to do is quiet, please. Let's just graph this function. So it looks like I'm going to pull this out. Man, my computer's going super slow today. Okay, we've got, I'm going to put this up in the top here, x to the 4th minus x to the 3rd minus 8, parentheses, divided by, parentheses, x squared minus x minus 6, end parenthesis. All right, so this, oh, that's right. This was that weird one that actually has stuff out here, doesn't it? Okay, so here's what we're going to do. Let's make it go, what is this? Let's go negative 10 to 10 and see if that works. Keep the y-axis the same, but let's go negative 10 to 10. X-axis, negative 10. Oh, yikes, what the heck is that? Negative 10 to 10. How's that look? That looks good. Let's go negative 5 to 5. That's going to be even better. Negative 5 to 5. And give me a little clearer picture. Okay. So here's my first screenshot. Right? Here. Now, it looks like the minimum value is here, right? This is just the y-intercept. Is that smaller? Yes, that's smaller. And then taller. And then here. So that's our first screenshot. Let me actually do it in here. And then I'll re-plug in. Send to current page. Okay. And then let's find the derivative. Now I had you guys find this by hand, right? No? Did I let you guys? Oh, this is number 4. That's right. Control C. D over dx of all this junk. Okay. So my second screenshot will have my x-intercepts, my minimums. There we are. Okay. This is my second screenshot. And then let's do that one more time. D over dx of all this junk. And this, I want just my x-intercepts. Now, is that going to cross the x-axis down here? Nope. Is it going to cross it right here? Yep. Is it going to cross it all the way down here? Nope. Okay, so really I only have 2 x-intercepts, here and here. And send to current page. Okay. Okay, so all that was just to get all of the important pieces on the screen. Let's write out the other pieces that you need to, say. Okay. So what is this telling me? This is telling me that I have along with this second graph, this is telling me where I can find my intervals of increase and then my intervals of decrease and where any maximum or minimum points may occur. Okay, because it looks like there's a minimum here, right? Looks like there's a minimum here and a minimum there. So negative 2.745. Actually, you know what? Let me give you just x values. Why are you doing that? Just doing that all morning too. Move that down. Let me give you just x values here. There's a minimum at x equals negative 2.745, and then again at 4.059. And it looks like there's another minimum value in here, but I'm just going to use my single derivative just to check. Okay, so taking a look in here, I see an x-intercept here of negative 2.745. Look at that, right there. I see an x-intercept of negative 0.807. Now, how do I tell whether that's a minimum or maximum value? It's going from above the x-axis to below the x-axis, which means it's going from increasing to decreasing, from positive to negative. If it goes increasing to decreasing, that's a maximum value. A maximum value at negative 0.807. X equals negative 0.807, which makes sense. Look, there it is. Now, where is there another x-intercept? Looks like there's another x-intercept right here at what is that, 0.411 there? Is that true? 0.411. Yeah, that's a maximum value maximum value, 0.441. Okay. Or is that a minimum? Ooh, shoot, is that a minimum? 0.411. Okay, we're right here. We're going from below the x-axis to above the x-axis. Is that a minimum? I might have to go back to my graph and zoom back in. I think that's a minimum value because it goes maximum. Yeah, that's got to be a minimum value. I'm sorry, I put that in the wrong spot. X equals 0.411. And then the 1.082, that's a maximum value. 1.082. Do I have all my maximums and minimums? Well, I highlighted 1, 2, 3, 4, 5 of them. And I have 5 listed there. Let's do the intervals of increase and decrease. Now, it's decreasing all the way to this negative 2.745. So decreasing from negative infinity to negative 2.745. I think I might need to extend this out because I think there's more intervals there. And then it increases from negative 2.745 all the way. See, now look, it's increasing, increasing, increasing. Does it ever decrease? It jumps, but does it decrease? No, it jumps down here all the way to negative 0.807. And then it starts to decrease from negative 0.807 down to 1.082. And then it starts to increase 1.082 till 0.411. Yes?
I think you have the 1.082 and the 411 flipped again.
Oh, duh. I did that. You're right. Yeah, but there we go. Yeah, because 0.411 comes before 1.082, doesn't it? Yes. 0.411 to 1.082. Okay. So we're here now, right? And then it starts to decrease. And then it decreases and then jumps and still decreases until this, right? So in decreasing, I have to add on another one from 1.082 until 4.059. And then at 4.059, it starts to increase and never stops. There's a lot on my screen, and it's going to be mad at me. That was a lot. Right? That was a lot of increasing and decreasing stuff. But I'm not done yet because I still have to identify the concave up and concave down and inflection points, right? Okay, so let's jump down here to my double derivative. Okay, concave up, concave down, and inflection points. Well, I only have two inflection points, right? I only have two inflection points at x equals negative 0.388 and x equals 0.79. 9. Yikes. 0.79. Okay, concave up versus concave down. Now, you can use your original graph to kind of see whether it's concave up or concave down. But remember that if it's above the x-axis, then it's concave up, right? If it's below the x-axis, then it's concave down. If it's above the x-axis, it's concave up. Below the x-axis, concave down. So it's negative infinity. Well, is it still concave up down here? No, it actually switched somewhere in there. And it's actually switching right there, isn't it? At x equals negative 2. It's concave up from negative infinity to negative 2. And then it goes concave down from negative 2 until negative 0.388. Concave up again, because it's above the x-axis, from negative 0.388 until 0.79. And then concave down again, 0.79 until when? 3. And then it jumps back above the x-axis from 3 onward. How do I know those are happening at negative 2 and 3? Look at the denominator of my original problem. Look at the denominator. See, this is where you have to use your algebraic skills along with what you see on the graph. What values do I have there that don't exist? Negative 2 and positive 3, right? I would factor the denominator to x minus 3, x plus 2, and then say, oh, well, that means x equals 3 and x equals negative 2 do not exist here. So that's why you see vertical asymptotes happening. And, I could think about that and go back up to my original. It was concave up to concave down to little bit of concave up to concave down to concave up, right? So there were actually a couple distinct pieces in here. Concave up with no inflection point, concave down with an inflection point, little bit of concave up with an inflection point, concave down, no inflection point, concave up. Why? Because we see asymptote, asymptote. Okay, so that's why it's shifting from concave up to concave down with no inflection point. That was a difficult one.
Can you scroll down?
Am I gonna be like the quiz?
On the quiz, I'm going to give you one that's more polynomially, more polynomic. I don't know if that's actually the word. Polynomialish. Polynomy.
So I have a question on number 6.
Okay.
So in my graph, right?
My answers are wrong, but I mean, just that's me. Yeah, I'm doing
The first one, this is the first one.
Mm-hmm.
And then it goes.
Look, can I pull up the key? Let me pull up the key. Let's go back to last year and pull up the key. Calculus, chapter 4. And I'm looking for 4-6 key. Oh, did I switch it all the way over already? 4-6 homework solutions. There we go. Yeah, boop. Come on. There we go. Yeah, I don't know if that's. I don't know if your graph is right there.
That's number 6.
Yeah.
Wait, mine was not.
This is what mine looks like.
Wait, what?
You have to change your graph a little bit to see the whole periodic piece of it. Yeah, look at my scale. I'm going from negative 30, or go from negative 20 to positive 20 with a Y scale in like the hundreds. Let me show you what I mean. Let me go back to Desmos. Let me graph this one for you guys too. Let me get this out of here. Let me go.
Oh, it's starting to look like that.
Yeah.
Oh, that's tough.
Oh gosh, mine did not look like that.
Yeah, there we go. Got it. Oh. That's like it's science on steroids. Yeah, I don't know.
What do we want here? We want this. 6 sine x minus x squared. Six sine x. Minus x squared. So you may be thinking that this is it. But remember that if it's trigonometric, come on.
From negative 30 to 30.
Yeah, it's going to start to wave out there. Let's go down here, and then let's go from negative. Let's go from negative 20 to 20. You see it waving now? I just zoomed out a bunch up into the hundreds. Like I made my lowest one, like go from like negative 700 to positive 300. That's fine too. I mean, yeah, I just made mine a little wider. I went from negative 20 to 20.
Whoa, there we go.
See now what I'm seeing here is I have multiple maximums and minimums there, right? So now when I go to d over dx of this, d over dx of Control C, V, and I do the same thing, d over dx of this. See, this is my derivative, right? Now, do I cross let's zoom in a little bit. Do I cross the x-axis here? Am I actually crossing the x-axis? I think I do. Yeah, I am crossing the x-axis. So I have an x-intercept, an x-intercept, and a minimum right here, right? Now, what does that mean in terms of my derivative? That means I have from increasing to decreasing, a maximum, inflection point, minimum, right? A maximum, an inflection point, and a minimum, right there. So you kind of have to like zoom in and see what else is going on. And then I really only have one more. So we had a max and a min and an inflection point in the middle. And then another maximum minimum point there. And that's the only places where it's going to be crossing the x-axis. So there's a minimum, increasing to decreasing, maximum, right? a maximum at 1.17. See, it's kind of hard to tell whether it's going to be a maximum or a minimum just by looking at the graph of the derivative, right? You kind of have to take the x value out of the intersection, or out of the x intercept, and then re-look back at my original graph. See, look here, 1.17. You knew something unique was going to happen at 1.17, so let's go back to my original. What's happening at 1.17? It's a maximum value. You see that?
Yeah.
And then you can see, well, I knew there was going to be something unique happening here and there. At negative 2.938 and then at negative 2.663. So let's go back. What's happening here? Okay. It's close, and we kind of have to zoom in. See, it might be actually better to go back here and look at that and see, okay, it was going from above the x-axis to below the x-axis to above the x-axis. And so you kind of have to use what you know about the derivative, the graph of the derivative, along with your original function to see what's going on. Now, in terms of the inflection points, inflection point, look at my inflection points that I'm going to have. Look at this. My inflection points are periodic. I'm going to have all those inflection points, right? So it must be something to do with the rotations of sine happening over and over and over and over again, okay? Did it give just the domain to work with? Yeah, from -5 to +3. From -5 to +3. So really, I was only focused on, where am I at? I was only focused on from here to here, right? So there's only just those inflection points happening. From here, that's actually turn off. I don't need all of these. Let me just do this. So from -5 to +3. Well, I guess I don't even need 3.481. Yeah. So I really only have 2 inflection points right there. -2.802 and -0.34. Now, how do I know whether it's concave up or concave down? Well, if it's above the x-axis on my double derivative, then it's concave up. If it's below the x-axis on my double derivative, then it's concave down. Concave down. So in this case, since I'm only focused on these 2 pieces, I know that it's concave down to concave up to concave down to concave up in the end until we get to, it's to 3, right? I'm sorry. So really I'm stopping before that point where it goes concave up again. So you kind of have to use your knowledge about the graphs. You think about the graph of the single derivative. Above the x-axis on the set graph of the single derivative is increasing. Below the x-axis on the single derivative is decreasing. Any intercepts of the single derivative, those are the maximum and minimum points of the original. Any maximum and minimum points of the derivative are possible inflection points. And then you could go with the double derivative and just look at the zeros, and that will tell you where the inflection points are. These should all have matching x values throughout, right? You should not be getting different x values each time you're switching from, the maximum and minimum points should be the same. Like these should connect. Like these x values should be the same, right? And then these x values should be the same. Because that's technically telling you the double prime or the zeros of the double prime are your maximum and minimum values of your single derivative, which actually relate back to the inflections, which you can't really click on for your single derivative. Okay? And this stuff will tell you your increase, decrease, as well as your maximum and minimum for your original. This stuff will tell you not only inflections, but concave up, and concave down. And inflections, okay? Got it? Okay, good. Just take a picture.
Hey, so that's gonna be great.
You crop me out? You crop me out?
Right.
Front center.
Appreciate it. Super sharp.
Push on Twitter.
Yeah, really. Hashtag ready like.
There's calc in the bed.
One of the only calcs in the Fed. Isn't that crazy?
That's
Like
true.
CCP calc, you guys understand? CCP calc is only offered at at Lake and Jackson. Isn't that crazy?
So we're literally better than Jackson.
Exactly.
It's just how the math.
This counts in the Fed.
There you go.
It's just better.
All right. And I've got a family friend that is taking CCP calc at Jackson. And I've heard that their teacher, like there's some medical stuff going on with their teacher. So she's like only posting videos and like a sub is in the room. And it's like she's only there like half the days and stuff. Yeah, I've been helping that person a lot. Okay, so what is on the quiz tomorrow? Remember that there's on the paper version of the quiz, there's two portions, right? One portion where I'm going to give you these calculators, right? And on the paper portion, the in-class portion, which is the, that's weird. Why is that doing that? There you go. That's on paper with the red calcs. Okay, that is really just section 4.5. Okay, and what will you have to do? 2 graphs by hand with just the red calculators. Okay, one on the front, one on the back. I am going to ask you because I didn't want to include a slant asymptote with a graph. Okay, so I just made it a separate problem. So there's 3 questions. I want to say about 3 questions on the paper copy. 2 graphs and then a slant asymptote problem. Okay, that's really it. And front side, one of the graphs, back side, one of the graphs, and then I just give you a little room at the top for the slant asymptote. That makes sense? Make sense? Question, Harbaugh?
Yeah, do we have to memorize the A, B, C, E?
No, I put it all in the question.
Okay.
Yeah.
Thank you.
You're welcome. Because that's, I don't know. You don't have to memorize that. The out of class portion is the stuff from section 4.6, and that's all Desmos. Okay. So basically, what's going to happen is I've already got an assignment waiting to be published. When you guys are taking the paper copy, I will publish that assignment. And basically, I gave 5 different polynomial functions. And you have to do basically everything that we did here. I want you to graph the single, the double, just the regular, the single, the double derivatives. And then also reveal any important pieces, just basically everything that we did right there. Reveal all the important pieces, and then state what the intervals of increase, decrease, maximum, minimum, concave up, concave down, and inflection points up. Does that make sense? I gave you I put on there 5 different polynomial functions, and then I assigned each of you one of them. Okay, I didn't want to have everybody doing the same one. So there are 5 different ones. So I think a couple of them are 3 people working on the same one. I tried to make pull them from different groups of people. You 3 are on doing the same one. Sorry to let you know. I know. I mean, but so I've assigned you each one. So just make sure you're doing the correct problem. Does that make sense? It's just one of them. Just one of them. And that will be due at 11:59 that night. I know many of you will just be like, "Oh, it's got to be due by the end of the night," but that's just the afternoon for Ian. So due by 11:59 p.m. You can put that in a Word doc. You can put that in a Google Doc. Just make sure you submit. I want screenshots. I want the 3 screenshots that you should know what we're doing here. The 3 screenshots with all of these points highlighted.
Do we do the derivative ourselves?
I'm okay if you don't.
Okay.
just because it's polynomial, and that's super easy.
Yeah.
You know what I mean?
Yeah.
So I really just am focused on the graphing piece of it.
Okay. Mm-hmm.
The graphing, and then you just have to, basically what I have here. Like this is like 2 was a polynomial, right?
Yeah.
This is what I want to see. I want to see the 3 graphs, all points, everything shown, increase, decrease, max, min. You only need to give me x values. Max, min, concave down, concave up, and where the inflection points are. Does that make sense?
Mm-hmm.
And I want to see all of those pieces revealed on the graph. Like if you say there's an inflection point at 0.26 and then 3.046, and then don't have those points revealed on your double derivative, then I'm going to take some points off because I need to see it on there. You might need to manipulate your window. Like look at this one. This window, was negative for the original, -7 to +7, going up from 6,000 down to -4,000. So know that you might have to manipulate your window depending upon how the graph looks. Okay, I just kind of threw these problems on there, randomly with the numbers on there. So it might look weird. That's okay. That's you got to figure that out. Questions about what's going to be on the quiz? This is a shorter quiz just because it's 2 sections. Shorter in terms of points, less point value. The other quizzes were like 40 points somewhere in there, and this one's like just 30. I think I give you like 10 points for each graph, a couple points for the slant asymptote problem, and then I think 10 or so points for the Desmos one for the whole assignment. Okay. Questions? Yeah, we good? Okay. I'm gonna stop the video then.
Can we do a slant asymptote problem before?
I have a quick question first.
Yeah. Well, I'll keep the video rolling.
No, just like. Okay.
What's up?
For number 6.
Yeah.
Stupid. Is there? I don't know if my window's right.
Let me see what you're working
Like, this is what I clipped. It's like, would that, or should I redo it?
No, that's okay. Just know that there was another one though. That's the problem.
Okay.
There's like you might not have seen all of the correct intervals, increase, decrease. Check these. If you found them correct, then you're good. Like you might be missing a piece.
Yeah.
You know what I mean?
Yeah.
Let's do a slant asymptote problem.
Yeah.
That sound good?
Yeah.
From the book.
We did 62 in class. Didn't you have to do 63 as well?
No.
No, let's do 63. Would you read that to me real quick?
Yeah.
6x what?
Okay, so 2x to the
Oh, I was
third.
way off. I'm doing 63, right?
Yeah.
Jeez, why did I say 6?
That's 64.
Oh, got it. So 2x to the,
Third.
okay,
Minus 5x squared plus 3x over.
hold on. This dang thing. Okay, plus 3x.
Yeah. Over an x squared minus x minus 2.
Okay. Now, how do I know that I could possibly have a slant asymptote? How do I know to check for a slant asymptote? Other than the directions are going to tell you to find the slant asymptote.
One difference between the numerator and denominator for powers.
Very good. Everybody hear that? How do you know if you even need to have a slant asymptote, or you need to check if there's a slant asymptote? The degree on the numerator is 1 bigger than the degree on the denominator. The degree on the numerator is 1 greater than the degree on the denominator. And now we long divide. X squared minus x minus 2. 2x to the third minus 5x squared plus 3x. And I'll add on a plus 0 on the end there. All right, so how do I make x squared look like 2x to the third? Multiply by 2x, right? So I say 2x times x squared is a 2x to the third. 2x times negative x is a negative 2x squared. 2x times negative 2 is a negative 4x. And we subtract. Everything cancels in my first term, which was the point. Negative 5 minus negative 2. So this is negative 5 plus 2, so negative 3. 3 minus a negative 4. So 3 plus 4 is 7x. Carry down our plus 0. How do I make x squared look like negative 3x squared? Multiply by negative 3. Negative 3 times x squared is a negative 3x squared. Negative 3 times negative x is a positive 3x. Negative 3 times negative 2 is a positive 6. And I subtract. So this gets me a 4x minus 6. And I can stop there because this is essentially 2x minus 3 plus 4x minus 6 over x squared minus x minus 2. How do I know I can stop? Because the degree down in my remainder is now less than the degree of what I was dividing by. And really, essentially, do I even have to calculate what the remainder is? No, because this, if I make x go to infinity, this will go to 0. Right? That will eventually cancel out because the degree on the bottom is bigger than the degree on the top. This is going to go to a number divided by a big number, which is essentially going to go to 0. So the slant asymptote is y is equal to 2x minus 3. That's the equation of the slant asymptote.
I just needed a refresher.
No, that's good. Okay, we feel good about that now? Okay. All right. I will stop the video now.